So the next thing that we want to talk about is how to go to macro level description. So let's say if you have micro description or if you have distribution description, how do you go to macro? So we'll introduce a few quantities. These are called moments, and there are various kinds of moments. You may be familiar with some of them. So the mean or the average is one moment. Then the variance is another moment. Then there's something called skew. That's also a moment. There's something called kurtosis. That's the fourth moment, and so on. So we'll look at, we'll define some of these and see how to calculate them. So the first one that we're going to look at is the mean or the average. And this is denoted by this symbol. So suppose the quantities that you're trying to measure are x. So the values you get are x1, x2, x3, x4, so on. So you're measuring x and you get these different values. How do you define the mean of them? So this is just, you add up all the xi's, I going from 1 to n, and then you divide by n. So, and this is something you're familiar with. You've been seeing this in school. This is how you find the average of all of these xi's. Now, so when I write it like this, so it means you know all the individual xi's. What that means is that this is the micro level description. So what you have done in this step is you have gone from micro to macro. You knew all the individual xi's, you added them up, divided by total number of data points you had, n, and that gave you the macro quantity of the mean or the average. But suppose you don't know that, but instead you know the distribution. So x1, x2, x3, in general these are your xi's, and you know how many times each one occurs. So which means you know the frequency of each one. So let's say x1 occurs w1 times, x2 occurs w2 times, x3 occurs w3 times, and so on. So you know each one's frequency. Then how do you calculate it? Then this is given by I going from 1 to the number of frequency bins, which I'm calling NF. So suppose you have F is the number of bins you have. So in your histogram you have F number of bars. Then when you add over them, then this becomes I called it W. So W I X I divided by N. Why W I X I? So Xi is coming 5 times. So Wi Xi is Xi plus Xi plus Xi plus Xi plus Xi 5 times. X2 is coming 10 times. So you're adding it 10 times. Basically, it's the same as this formula. Just instead of adding them individually, you're saying I'm adding 5 times x1, 10 times x2, 3 times x3, 4 times x4, 9 times x5, and so on. So that's all I'm doing. I'm just writing it in terms of their frequencies. So the Wi over here are the frequencies of getting xi. So then this is the formula in terms of this distribution. So in this formula, well, then I shouldn't write n because I don't know what is the total n, but I do know this is summation wi. I again going from 1 to nf. So again, because if I add up this whole histogram, then I will get the total number of points only, in the end. So this is the formula that takes you from a distribution description to the macro state description. So here's how you do it from both starting from micro or starting from distribution. This is how you can calculate what is the mean. Now let's take this to the continuous limit. So if you have a continuous variable, if your x is continuous, then instead of, so the same formula in terms of the wi xi, this becomes, so the sum becomes an integral, and the wi, the histogram frequency, becomes the probability density distribution. So px x divided by, in the denominator it is just this, px. So exactly that, w becomes p, xi becomes x, and the sum becomes an integral. So this is what you do when you have a continuous variable. This also allows you actually to generalize to any function. Suppose instead of taking average of x, if I was interested in taking average of x square, means this graph shows how all the x's are distributed. I want to ask how are the x squares distributed? What is the average of the x squares, not of x? So then basically instead of x over here I will put x square. So integral px x square dx divided by integral px dx. In general, any function, not just x square, if I want to take the average of some function g of x, then this is just integral p of x g of x dx divided by integral p of x dx. So general formula, if you know how the x's are distributed and you want to know the average value of some function of x, here is the way to calculate that average. So this was to do with means. We can talk about the next moment, which is variance. Variance, one common way of remembering how to define variance is it is average of square minus square of average. What is average of square? So once again you have all your xi's. So the average of the squares, so you defined average of the squares. Same way as we saw last time on the previous page. So this is just so average of the squares of x. And what is square of average of x? So average of x, square of that. So average of x is this, then square of this entire thing. So when you take this difference between the two, you get the variance. And variance is called sigma square. Why is it called sigma square? Because square root of the variance will turn out to be the standard deviation. So sigma square is basically average of square minus square of average, which is so this is your formula. And standard deviation, as I said, is defined as square root of the variance. There is one more way of defining the standard deviation, which is as follows. So if the average of all your xi points is called this, then how much is the deviation for each xi? So deviation of the ith point is just xi minus the average. This is how much it deviates from the average. And then if I take the average of this, so if I take the average deviation, this is going to be average of all of these xi's minus this. So this is average of yes, and then if I take the square of this, that turns out to be the variance. So let's check. So what is the, so this becomes, well, so it's the square average of the square of this. So I'm looking for deviation squares average. Correct. So this is summation xi square minus 2xix plus this divided by the total number of points, which is xi square divided by n minus, now notice over here that this comes out because this average is just some constant, and then sum over xi divided by n is just the average itself, and then over here again average is just some constant which comes out, n also is some average which is some constant which comes out, and then over here you're just left with summation 1 going from 1 to n. So summation 1 from 1 to n is just n. So you're left with, so this over here is the average of the squares, and over here minus 2x square plus x square, this is minus x square. So you can see again this is just average of square minus square of average. So this is just the sigma square. So this is one more way of defining what is the standard deviation. It is the average of the square of the deviation in for each of these xi's. Okay. Now there is one subtle point that I want to bring up over here. So when I say that sigma square is just the average of x minus its average square, so average of the deviations, average of the deviation squares. In some books or in some contexts over here, instead of n you will find it is n minus 1. So there is a very subtle point regarding why it is n versus n minus 1. It has to do with degrees of freedom. I don't think I want to discuss that right now. Anyway, in your math physics, in your mathematical methods 2 course, we will be discussing statistics in a little bit of detail. So at that point, I think we will talk about this. But right now, let's not bother about whether it is n or n minus 1. Anyway, if you're trying to do some sort of statistical analysis, so if you're trying to find standard deviation of some data set, your number of data points had better be large. So n should typically be a large number. And if n is a large number, then whether it's n or n minus 1 doesn't make that much difference to your standard deviation or your variance. Or another way of looking at it is, if your n is small, so small that it makes a difference whether you're using n or n minus 1, then you actually ideally should not be doing statistics with this data set. In order to do any statistical analysis, you need large amount of data. Only then your mean, variance, all of these will make sense. If you're doing it with a small value of n, then you might as well not do it. So it doesn't matter whether it's n or n plus or n minus 1, because it won't make much difference to your standard deviation. Achha, what is the physical meaning of mean and variance? So mean basically tells you, so if you have some distribution, mean tells you, what does mean tell you? Mean is mean. You know what average means. It's some in between value of x. Yeah, it's literally what's between the lowest points and the highest points. That's the mean. It tries to tell you where does the center of your distribution lie in some sense. On the other hand, you can look at something called the median. Median will tell you what is the midpoint in terms of in terms of there being equal number of points on the left and on the right of this. So that is the median. And then the third quantity that you can talk about is the mode. Mode just tells you where is the peak of your distribution. Or the most frequent value of x. So these three tell you three very different things about your distribution. On the other hand, standard deviation tells you how much is the spread of the distribution. So for example, if you have a small value of standard deviation, then it means all of your values are very closely spaced. So it might be something like this. On the other hand, if you have a large value of sigma, it means it's a very broad, spread out distribution. So this is what mean and standard deviation signifies for any kind of distribution. How useful they are depends on the kind of distribution. There is no general answer as to which one is useful. So for example, if we go back to those distributions that we drew, so for a distribution like this one, like the first one, mean might not necessarily make sense because you have a large number of points at small l, very few points at large L, and okay, sure, you can calculate what the mean is. Mean will probably pull it, the data will pull the mean towards the left because there are more points over there. What that necessarily means is up to you. You can interpret that. On the other hand, if you're looking at something like the height of people, this one, then it makes sense to talk about mean because most of the values are spread out around some central value, which might be the mean. Also in this case, then it also makes sense to talk about what is the standard deviation because that tells you how much is it spaced out. Are most people lying between, let's say, 150 centimeters and 200 centimeters? Or are most of them just between 170 and 180? It tells you how broadly your values are spread. If you look at this distribution over here, mean is absolutely useless because if you take the mean time, then you'll get something over here, but there are actually very few points over there. That's because this distribution has two peaks. Or in general, if not necessarily two, but if you have a distribution which has multiple peaks, mean may not necessarily make much sense to use. It might not actually physically signify anything. Same with mode. Over here, what does mode mean? Because there are two maxima. Maybe one of them is bigger than the other. Maybe people mostly go for dinner, not too much for lunch at the restaurant. But still, it's going to be skewed towards one side of it. So using mean over there, or using mode over there again might not make sense. So it depends on what kind of distribution you have. You should accordingly use what kind of you should use the kind of quantity that makes physical sense. Okay, so this was the variance and standard deviation. Then there's one more quantity which is the skew. Not so commonly used. How is skew defined? Skew is defined as the average of this quantity. So it has skew. When you're calculating mean only contains linear terms in x. When you're calculating standard deviation, you involve squares, and when you are calculating the skew, you start to involve cubic power, third power of x. Skew tells you in which direction your distribution is bent. So for example, if you have a distribution that looks like this, so this has a negative value of skew. But if you have a distribution that looks like this has a positive value of skew. So it tells you, so, and if you have a perfectly symmetric distribution, then for this skew will be 0. So skew is telling you how much your distribution deviates from being perfectly symmetric. How is it bent towards the left? Is it bent towards the right? That is what skew tells you. Alright. So these are the moments that I wanted to talk about. The next thing I want to discuss is the covariance. So far we have been discussing distributions of one variable. So there is only x, or only velocity, or only height, or something like that. Now we can talk about distributions in 2 dimensions or multiple dimensions. So suppose there is an x variable and a y variable, and you want to find out how they are correlated. So we'll talk about correlation coefficient in a bit. But the first step to doing that is to define something called a covariance. So you can define the covariance of x and y, and this is defined as the average of xi minus average of x times yi minus average of y. So this is the definition of covariance. And in fact, so you can calculate this. No? So this is average of xi yi minus xi average y minus average of x yi plus average x average y. So this will turn out to be average of xi yi minus average y is just some constant number. So pull it out. What you're left with inside is average of x minus, again, average of x is constant, pull it out. What you're left with inside is average of y. And over here, average x, average y both are constant. So their average is just that itself. So in the end, well, some of these will, 2 of these can cancel out. And you're left with average of x y minus average x average y. What is this? How do you calculate this? This is just going to be so that's how you calculate the covariance. Now once you have calculated the covariance, you can calculate something called the correlation coefficient. And correlation coefficient defined by it's denoted by rho of xy is covariance of xy divided by the standard deviations of x and y. Oh, one thing I should say over here, if you notice, so looking from this formula over here, notice that covariance of x and x is just going to be average of xi minus average x square, and this is nothing but the variance in x. So in some sense, the variance is a special case of the covariance, or covariance is a generalization of variance when you have multiple variables in your system. So this is the correlation coefficient that we have defined. What is the big deal about this? What does this denote? So suppose you have your two-dimensional space which has x and y, and you want to see how your points are distributed. Now if your points are distributed like this, so clearly there seems that there is some relation between x and y. So in this case, your correlation coefficient will turn out to be positive, in fact close to 1. And then we say that x and y are correlated, because when x increases, y also increases. I'm not necessarily saying that there is a causal relation between them. I'm not saying that y is increasing because x is increasing, or x is increasing because y is increasing. That is called causality. I'm not concerned about causality. I'm just talking about there being some correlation. Both of them are increasing at the same time. Whether or not it's because of each other, that's a separate issue. You can also have a case where they are distributed like this. So now what happens is, when x increases, y decreases, or when x decreases, y increases. So in this case, this correlation coefficient turns out to be negative, and then we say this is that these two variables are anti-correlated. And of course, you can also have a situation where x and y don't have anything to do with each other. So if the distribution looks like this, then clearly the y value doesn't particularly depend on x value, or x value doesn't depend on y value. So in this case, this correlation coefficient will turn out to be close to 0, and we will say that these two variables are uncorrelated. So if you want to understand what kind of correlation there exists between two variables, then that's when you can use this correlation coefficient.